We're now ready to discuss tangent planes and linear approximations. This is similar to what we did in Calculus 1. In Calculus 1, we took a look at curves in two-dimensional space in the xy plane, and we evaluated tangent lines to those curves. Let me draw an example of this so that we can sort of see and remind ourselves of what we're talking about. In two-dimensional space, you might have some kind of curve that does something like this. And when you're looking at it, you can visualize, if you will, a tangent line to the curve at a particular point. So the tangent line barely touches the curve at just one point. In some sense, it's almost like over this very, very tiny little interval, it's almost parallel to the curve at that point. Now, this implies that the curve is differentiable, which also means it's continuous and it doesn't have a vertical tangent line or a sharp corner or a cusp. And because of that, if you zoom in really close on that one point where they connect, then it becomes nearly linear. And that's what we mean by saying the tangent line is sort of parallel to the curve at that point. When we get into three-dimensional space, the situation gets a lot more complex. The tangent line to a point on a surface in three-dimensional space is no longer unique. In two-dimensional space, the tangent line is unique. It touches the curve at one point and has a specific slope given by the first derivative of the function at that point. However, when we're in three-dimensional space, and let's say that we have an ellipsoid, so this is an ellipsoid, and I want to know what the tangent line is at this point here on the ellipsoid. So let's see, I'll hold it to the side. The problem is I could spin the tangent line in 360 degrees. In other words, I can spin it all the way around and yet maintain the same slant and be touching the surface at the same point. So there are infinitely many tangent lines that touch the surface at that point. If that's no longer unique, it doesn't serve us a lot of good if we want to approximate values on the surface by using that line instead. Remember that we were able to do this in Calculus 1. What does turn out to be unique is the tangent plane. So again, if I'm looking at my ellipsoid and I'm touching at one point, it turns out that the tangent plane, which I'm using a flat sheet of cardboard for the tangent plane, the tangent plane is unique. In a sense, it consists of all of those infinitely many tangent lines spinning around in all directions. So we want to take what we've learned previously about finding the equation of a tangent plane and apply it to approximating values on a surface in three-dimensional space using the values on the tangent plane instead. And again, as long as I'm very close to the point where the tangent plane was calculated, then those should be decent approximations of the value that's on the surface. But the equation of the tangent plane could turn out to be much simpler than the equation for the three-dimensional surface. Let me share my screen with you, and we'll get started taking a look at tangent planes and linear approximations. Now that we're in three-dimensional space, we can think of the set of all those tangent lines spinning around, touching the surface at one point, as lying within the single plane called the tangent plane. We can think about the tangent plane in a sense being parallel to the surface at that point. And again, this is similar to the idea that the tangent line in two-dimensional space was somehow parallel to the curve at that point. It does require differentiability because that means that as you zoom in on that point, both the surface and the curve become more and more, well, linear, flat, if you will. What we want to do now is think about the way that these tangent planes are created. So again, if I take my piece of cardboard and I am assuming it's touching my surface, there are infinitely many tangent lines that spin around the same point. And it's very hard to spin this with just two hands. But again, if it's fixed at one point, there are infinitely many lines that spin around that point. It's almost like a spinner in a board game. The board itself, the spinner board, is the tangent plane, and the spinner, as you spin it, represents all the possible tangent lines to the surface at the point where the spinner is attached to the board. And all of these tangent lines make up the plane. Let's now go ahead and take a look at a picture that shows it in well, sort of trying to show 3 dimensions, but in a 2-dimensional space. So we have a curving surface here, S, which is shown in orange. And we have a tangent plane, which is represented in this light blue color. There is a point in black called X naught, Y naught, Z naught. And this point is where the tangent plane barely touches the surface at that one point. Then what we have is curves that pass through that point. But within the tangent plane, we have tangent lines that attach here and spin around in all directions, generating the tangent plane. Let's formally define the tangent plane now. We have our point, X naught, Y naught, Z naught, and it's a point on some surface. And we're going to let C be any curve that passes through that point, but lies within the surface. So going back to our picture up here, the curve C is sort of shown here in a darker red color. It is within the surface. It's on the surface. So if we have an ellipsoid, it's on the surface of the ellipsoid. It's not a tangent line. It's a curve that lies on the surface but goes through our point P naught. If we take any such curve in the surface that goes through that point P, then we can say that all the tangent lines to all such curves C at that point lie in the same plane, and that plane is called the tangent plane. Now we'll see some conditions in order for all of the tangent lines to lie within one plane. And as you might expect, it's going to be somewhat similar to the 2-dimensional case. When do we not have a unique tangent line? Corners and cusps. So you can imagine if you had a surface that came up to a sharp corner, you're not going to be able to get a unique tangent plane because it will, well, wobble in all directions around that pointy part, if you will. So if the tangent lines to all the curves in the surface that go through the point P do lie in the same plane, then that plane is called the tangent plane. Let's see if I can find something here that is pointy so I can demonstrate. All right, so I have a water bottle here with a handle, and on the handle, it comes to a sharp corner. If I take my piece of cardboard and I try to find a tangent plane, well, it wobbles all around on that sharp corner. There's no one unique tangent plane at that point. And we'll find the conditions for the tangent plane to exist in a little bit. Now let's remind ourselves of what we learned earlier in this semester about the equation for a plane. The equation for a plane requires that we know one point in the plane, which generally is going to be the point where it intersects our surface, X naught, Y naught, Z naught, and we need a normal vector to the plane. This would be a vector that comes off of the plane at a 90-degree angle, right? It is normal to the surface. So it could point up, it could point down. Remember, vectors point in one direction, lines point in both. The normal vector is given by A, B, c. If we solve that equation for the variable z, we get the equation that you see here, that z is equal to z naught, the z value at that point, minus a over c, the ratio of the first and third components of the normal vector, times x minus x naught, minus b divided by c, the ratio of the second two components of the normal vector, multiplied by y minus y naught. Now, we're going to define uppercase letter A to be this negative A over C, and uppercase letter B to be this negative B divided by C. This will allow us to rewrite the equation of the tangent plane solved for the dependent variable Z, where all the terms are positive, which, as you know, we kind of prefer. But what are these uppercase letters A and B? What is it they represent? To figure this out, the first thing we want to do is we want to make one of the variable values constant, much as we did in the previous section when we were looking for equations of tangent lines to a trace, the intersection between a surface and a plane that was parallel to X or Y. In this case, we're going to start by saying we're going to hold y to be constant. So we're allowing x to vary, but y is not going to vary. In that case, since we want it to connect at that point, we set the y value to be y naught. And then y naught minus y naught gives us 0. So this third term drops out of the equation. When it drops out of the equation, we end up with z equal to the function value at x naught, y naught, which is our z naught, plus uppercase letter A times x minus x naught. So remember, this is z equal to z naught plus A times x minus x naught. Now, this is just the equation of a line, right? So what line must it be? Well, I held y constant and I allowed x to vary. So this must be the tangent line to the trace, which means that the slope is the partial derivative with respect to x. But the slope in this equation is uppercase letter A. And that must mean that A is the first partial derivative of the function with respect to x evaluated at that point, x naught, y naught. We can do a similar thing by allowing y to vary and fixing x to be a constant value. Then x naught minus x naught gives us 0, and the first term, or rather the middle term, would drop out of the equation that you see up here, right? The next thing that we want to take a look at after we've got this, and we're going to find that in that case, we're able to solve for b as the first partial derivative of the function with respect to y, evaluated at the point x naught, y naught in the domain. This gives us a new equation for the tangent plane at that point, z equal to the function value at x naught, y naught, which is just z naught, plus the first partial of x evaluated at that point in the plane, multiplied by x minus x naught, plus the first partial with respect to y at that point from the domain, times y minus y naught. Now, let's go ahead and take a look at an example. And I think I forgot to share my screen, so let me do that now. This example comes out of section 4.2. It is a quadric surface. We have a function g given in terms of x and y as negative x squared minus y squared plus 2x plus 4y minus 1. In order to find the tangent plane, we need to find the first partial derivatives with respect to x and with respect to y. The first partial with respect to x is negative 2x plus 2, and the first partial with respect to y would be negative 2y plus 4. Now we're going to choose a point in the domain of this function, and the domain of this function is, of course, the entire R2, the entire xy plane. There's no restrictions on what x and y can be. So we're picking the point from the domain, from the xy plane, which we always visualize as our floor, being 3, 3. We evaluate the partial derivatives at that point to get that the first partial with respect to x is negative 4, and the first partial with respect to y is negative 2. Now, in order to complete the equation of the tangent plane, we also need the value of z naught. In other words, we need to know what the z value is right there at the point where the plane connects with the surface. To find that, we substitute the domain ordered pair 3, 3 into the definition for the function, and that will give you negative 1. So our point on the surface in three-dimensional space is 3, 3, negative 1. Now we take our formula and we replace g of x naught, y naught with the z naught value of negative 1. We replace the first partial at the domain point 3, 3 with negative 4, and we replace the first partial with respect to y at the domain value 3, 3 with negative 2. We also want to use the values that we used from the domain inside our formula to replace x naught and y naught. And if you multiply this out, you will get negative 4x minus 2y plus 17. Let's go ahead and take a look at what it looks like in CalcPlot 3D. You can see a still image of it out there in your lecture notes. Here's an image of it in CalcPlot 3D. If you turn it so that the tangent plane is sort of, well, coming straight out of the board at you, and it's very difficult to get it exactly right, you can tell that the yellow spot is pointing out of both sides, meaning that it connects there and it's coming through the plane and the surface at both points. This tells us that the tangent plane is connecting right there. As long as I am close to this yellow point, we'll see later in this lecture that we're able to approximate values on the surface, on the paraboloid, with values that are on the tangent plane instead. Let's now take a look at example 1. In example 1, we want to repeat the process of what we just did, and we want to find the equation of the tangent plane to this new function given by x cubed minus x squared y plus y squared minus 2x plus 3y minus 2, and we're given the point in the domain of negative 1, 3. In other words, that's coming out of R2, the xy plane. In order to compute this, we need to find the function value at negative 1, 3. That will give us our z naught. We need to find the first partial of this with respect to x, also at that point from the domain. And we need to find the first partial with respect to y at that point out of the domain. Then we'll replace x naught with negative 1 and y naught with 3. Go ahead and pause the video now to work out the calculus and then turn the video back on and we'll compare our results. So let's compare. First thing I did was find the value of the surface at the domain ordered pair negative 1, 3, which gave me 14. Then I took the first partial with respect to x, which gave me 3x squared minus 2xy minus 2. I then evaluated that at the domain point, or you can think of it as evaluating it at the point on the surface, same thing. You get 7. All right, that's the slope of the tangent line of the trace at that point where we hold y to be constant, y equal 3. Now we take the first partial with respect to y, which gives us negative x squared plus 2y plus 3, and evaluate that at the domain point or the point on the surface, and we obtain 8, which is the slope of the tangent line to the trace where we allow y to vary, but x is held constant at -1. Then we have all the pieces that we need in order to complete the equation, and we substitute it into our equation formula. Let me scroll it down just a hair, which is up here in dark blue. This gives us 14 plus 7 times the quantity x minus a -1 or x plus 1, plus 8 times the quantity y minus 3. When you multiply it out, you get z equals 7x plus 8y minus 3. At the point where we have -1, 3, 14, this tangent plane barely skims the surface of this three-dimensional surface. Let's take a look at it out here on CalcPlot 3D. This is a really interesting shape, the function itself. I'm going to take the tangent plane and hide it for just a moment so we can see what this shape looks like. Notice how it has a point here which dips down lower than all the others, and one here which seems to be higher than the ones closer around. We're going to be finding these in the not too distant future when we look for maxima and minima. Yes, we can find maxima and minima in 3 dimensions as well. You know this. We have mountaintops and we have valleys. Those are maxima and minima in 3-dimensional space. This is a really interesting shape here. It's kind of fun to play with this one, and we'll play with it again. In yellow, you see the point that we're interested in. And when I graph the plane, you can see that the point is on both the plane and on the surface. That plane is tangent in some sense to the surface at that point, sort of parallel, if you will. We're now going to turn our attention to using the tangent plane to approximate the z value. This is going to be called linear approximation. In this case, the approximating function is actually the tangent plane, which, while it's not a line, in a sense is generated by infinitely many tangent lines. So we're going to use the tangent plane to approximate values on the surface that are close to the point where we computed the value of the tangent plane. In Calculus 1, we did this by using the tangent line to approximate the value on a function close to the curve. So when we were looking at this, we said that the y value on the function was approximately equal to the value on a function we called L of x, where L stood for linear approximation function. But really, it's just the tangent line at the point a f of a. So we have the y value f of a, x minus a, and f prime of a representing the slope of the tangent line. When we used this, we were able to approximate values on the function by instead using values on the tangent line. When the curve is really complicated, this can be a simpler way of approximating values on the curve. In other words, if I want to approximate a value, say here on the blue curve, I could instead use the value on the tangent line and have that be my approximation for the value that's actually on the curve. This is what we did in Calculus 1. Now, you may remember in Calculus 1 that the actual change in the y value from, say, the black point to the blue point was delta y. But dy is how we define the differential, and the differential was the difference in the y value on the tangent line between the black point and the blue x. That is how we define the differential dy. Let's now scroll down to see how we do this with the tangent plane. We still call it a linear approximation, and we'll still use L as the name of the function, but it's now a function of two independent variables since we're in three-dimensional space. And we're using the equation of the tangent plane as our approximating function. So we can approximate the value of g of xy as long as we're close to the point that generated the tangent plane. Here's the formal definition of the linear approximation function in 3 dimensions. We're given a function z as a function of x and y, and we're told that it has continuous partial derivatives that exist at the point x naught, y naught coming from the domain R2 or some subset of R2, the xy plane. The linear approximation of that function at the point from the domain is given by the tangent plane at that point. Let's look at a picture that sort of demonstrates what we're trying to do. You see a sort of, well, it looks kind of like a P to me. It's not too dissimilar from the ellipsoid shape we had earlier, but we can see that there's a tangent plane in light blue, and there is a point coming from the domain. The domain point is down here in the XY plane, XY, and you see a dashed line connecting at a red dot that is on both the tangent plane and the surface. We want to approximate the value, the z value, the dependent variable, at another point on the surface, which is given by this red dot here, below and to the left. What we're going to do, though, is we're going to use the red dot that's on the tangent plane, but not on the surface, to approximate this other point on the surface. So what we're doing is we're scooting over a little bit in the x direction, x plus delta x, and scooting over a little bit in the y direction, y plus delta y, to get our linear approximation on the tangent plane for the actual point that is up there on the surface. Here's another image of one that's being applied to a paraboloid. And when you're looking at the paraboloid, again, what you're visualizing is that you have a point on the surface where you calculate a tangent plane. You want to approximate the value at a different point on the surface, but close to where you calculated the tangent plane. Then you can use the value that's on the tangent plane to approximate the value on the surface. Now, this only really makes sense to do when we have complicated surfaces and we're relatively close to the point at which we found the tangent plane. We're now ready to try an example. In example 2, we're given a function of two variables in three-dimensional space, e to the power 5 minus 2x plus 3y. And we're asked to approximate the value of the function on the surface at 4.1, 0.9 by using the tangent plane at the point 4, 1 instead. And we want to find what the approximate value of the function is by using the value on the tangent plane instead. So what we need to do first is, of course, find the equation of the tangent plane at the point 4, 1. That, again, is coming out of the domain, R2, the xy plane. So we need to compute what the function value is at 4, 1. That will give us our z naught value, the first partial derivative there with respect to x, and the first partial derivative there with respect to y. Then we'll replace x naught with 4 and y naught with 1. After we've done that, we'll have the equation of the tangent plane, and we can then substitute the values 4.1 and 0.9 into the tangent plane to approximate what the value is there on the function at the point by using the tangent plane approximation instead. Go ahead and pause the video to work this out, then turn the video back on so we can compare our results. When we find the equation of the tangent plane, we start by finding the value of the dependent variable at the domain ordered pair 4, 1. This ends up giving us e to the 0th power, which is the number 1. This gives us the ordered triple 4, 1, 1 as the point on the surface at which we want to find and calculate the tangent plane. Now we find the partial derivative with respect to x, and this will give us -2 times the exponential e to the 5 minus 2x plus 3y. When we evaluate that at our point from the domain or on the surface, again, the exponential becomes 1 and we get -2. When we do the same thing, but taking the partial with respect to y, we get 3 times the exponential. And since the exponential at that point becomes e to the 0, we get 3 for the partial derivative with respect to y. The next thing that we do is we put these together into the equation for the tangent plane. The equation for the tangent plane is seen right here. Once we put those values into the equation for the tangent plane and simplify, we get z equals -2x plus 3y plus 6. This is the equation of the tangent plane or the linear approximation function. We want to use the tangent plane to approximate the value on the surface when x is 4.1 and y is 0.9. Substituting those values into the tangent plane equation, we end up with a value of 1/2. 1/2 is the linear approximation for the surface, the function at that point. This is an approximation for the true value on the surface itself. If we calculate the value, the true value on the surface itself, we find that it comes out to be e to the -1/2 power. This gives us the approximation 0.607. So it's not as accurate as we might like, but then again, we're 1/10 of a point away. To make the approximation more accurate, we need to get closer to the point. How close you need to be to the point depends on how much change in curvature there is at that point. The more nearly, well, plane-like the surface is at that point, the further away you can move and still have a good approximation. The less plane-like it is at that point, the closer you need to be at the point to have a good approximation. Let's look at this one on CalcPlot 3D. It's quite difficult, and I had to play around quite a bit with the x and y axes and also the scale to make it make sense. The graph of the function, e to the power, is here in green. The tangent plane is graphed in gray. If you turn it on its side, you can see that the yellow dot is where the tangent plane connects with the surface at that point. The pink dot represents our linear approximation value, the 1/2, on the tangent plane, but is not actually on the surface. The true value of it is the blue dot, which is actually on the surface itself. The next thing we want to talk about is when do we have a tangent plane exist, a unique one, and when do we not? Just as there are occasions in functions of one variable where a unique tangent line does not exist, there are going to be occasions in three-dimensional space where a unique tangent plane does not exist. An example in functions of one variable would be the absolute value function. has a corner at the origin, meaning it's not differentiable there. So there's no unique tangent line because you don't know which way to draw the line. It's a very similar occasion in three-dimensional space, all right? We need to define basically when that occurs, and that's going to be when it's not differentiable there. The same situation as we saw in the two-dimensional case. But in order to do that, we have to define what we mean by differentiable at a point in three-dimensional space. This is connected to the idea of the smoothness at that point. In the two-dimensional case, it meant no corners or cusps. In the three-dimensional case, a smooth curve is one where the tangent plane exists at that point, which is sort of a circular definition. How do you know the tangent plane exists? It's smooth. How do you know it's smooth? You have a tangent plane at that point. For a vector-valued function, remember that we define smoothness as any curve for which the first derivative of r was continuous and not equal to the zero vector for any value of the parameter t. Let's go ahead and continue discussing differentiability by making differentiability at a point more precise. A function is differentiable at a point if for all points in a delta disk around the point in the domain, we can write an equation for the tangent plane at the point plus some e of xy, where e of xy is in fact a error term. So when we're looking at this error term, we want to evaluate what happens. The error term must cause this relationship here to go to 0 for it to be differentiable at the point. If the error term is going to 0, that basically implies that we have a tangent plane at that point. Now, if you look at the denominator, we have this error term, and in the denominator, we have the square root of x minus x naught squared plus y minus y naught squared. When we look at this, realize that this is simply giving us, of course, the distance between the point xy and the point x naught y naught in the domain plane, which is R2. We want to take the limit of this as xy approaches x naught y naught. Remember that when you're evaluating a limit with a function of two independent variables, it's very difficult to prove that it exists if when you substitute in the values, you do not get a finite real number. If you get a finite real number, you're done. If you don't, then the best you can generally do is prove that it does not exist by looking at different paths. This is not a formula that we're going to be using a great deal, but you can find one in the textbook. Let's take a look at one of the ones out of the textbook so that you can see how this might work in practice. In this example, we have the function f of xy equal to 2x squared minus 4y, and we want to prove that it is differentiable at the point 2, -3. How do we define this error term, e, as a function of xy? And this is uppercase letter E, not Euler's number. First, we need to calculate the three pieces that we need to find the equation of the tangent plane at that point, provided it exists. Our point in the plane, the domain, is 2, -3. We first substitute those values into the function to get the function value at that point. Then this will give us the value of 20. Then we compute the first derivative of the function with respect to x, the partial derivative. This gives us 4x, and when we substitute the value from the domain, we end up with 8. Next, we find the partial derivative with respect to y of the function, which is, well, -4. It's always -4 at any value. So we now have the three pieces to write the equation of the tangent plane at the point, provided it exists. Substituting these values in, we have 20 plus 8 times the quantity x minus 2 minus 4 times the quantity y plus 3 plus our error term. Now the question is, how are we going to find the error term? Remember that what we are doing is we're representing the function itself as this tangent plane plus the error term. That means we can replace the function with 2x squared minus 4y, and we can multiply out and distribute our constants on the right side. When we do this, this gives us an equation in x and y plus the error term. Finally, we solve for the error term to get 2x squared minus 8x plus 8. This will enable us to put it into that equation or into that formula where we have the error term divided by the distance between x, y, and the specific point we're interested in. In this case, our specific point from the domain was 2, -3. So we're looking at the limit as x, y, some arbitrary value, hopefully in a delta disk nearby, approaches 2, -3 of the error function 2x squared minus 8x plus 8 divided by the distance between x, y, and the ordered pair 2, -3. The next part, of course, mostly involves algebra, going ahead and simplifying the different pieces. You'll see here the first thing they did was factor out the common factor of 2 from the error term in the numerator. The next thing they did was to factor the trinomial in the error term as the quantity x minus 2 squared. Once they had this, then they went ahead and evaluated, looking at the ratio of what we have on top and what we have on the bottom. Now, how did they come up with this term right here? They need to find something that will enable them to show that the limit is going to 0. In order to do that, they need to somehow simplify this algebraically, but there is no means of simplifying it algebraically. So what they did instead was found an expression that they could simplify algebraically that was larger than the original expression. So they added in a term that did not appear in the original limit. This is the term 2 times the quantity y plus 3 squared. And note that it is not an equality symbol, but an inequality less than or equal to. Because the y plus 3 is squared, we know that it's strictly positive, and multiplying it by 2 again makes it strictly positive. So we're adding a positive value to the numerator, which will make it a larger value. And this is why the inequality points in the direction that it does. However, this gives us the same expression that we see underneath the radical. And then we're able to reduce them, giving us 2 times the square root of quantity x minus 2 squared plus the quantity y plus 3 squared. Finally, we are now at a point where we've finished the algebra and we can actually do the calculus, which is to substitute the values x equal 2 and y equal -3 into the expression. Once we do that, we see that we get 2 times the square root of 0, which of course is 0. This means that it is differentiable at the point, and there is a tangent plane at the point. Let's take a look at differentiability and continuity. In the case of a function of one independent variable, we know if it's differentiable, then it must be continuous. But this implication only goes in one direction. It does not go in the reverse direction. We've already seen the graph of the absolute value function, which is definitely continuous at the origin where the corner is. but it is not differentiable there. Let's go ahead and see what happens in the three-dimensional case. Is there a case where we have differentiability implying continuity again? If differentiable, then continuous. In this case, we let z be a function of two independent variables with a point x naught, y naught in its domain. If the function is differentiable at the point, then it must be continuous at the point. In other words, the same implication holds in the three-dimensional case that held in the two-dimensional. In the two-dimensional case, however, the implication did not go the other direction. Just because it was continuous did not mean it was differentiable. In the case where we have functions of two independent variables, there is a condition under which differentiability does imply, or rather continuity does imply differentiability. This is very different from a function of a single variable. Again, we let z be a function of two independent variables with a point x naught, y naught in the domain. If the function and the first partial derivative with respect to x and the first partial derivative with respect to y all exist in some delta disk around the point x naught, y naught, and they're continuous at the point x naught, y naught, then the function is differentiable at that point. So if the first partial derivatives with respect to x and with respect to y are continuous at that point, and the function exists at the point, then we know that it's differentiable there. This is a much easier way to establish differentiability than computing the error term and finding that limit. Let's now look at a short section at the end of this particular section. This is on differentials. Now, in Calculus 1, as we discussed earlier, we defined the differential dy to be the derivative of the function, the first derivative, multiplied by the differential dx. This was created by an abuse of notation where we took dy dx, abused the notation, and swung the dx to the other side. However, we also noted that dy was not equivalent to delta y. Remember when we were talking earlier, dy is the difference in the y values on the tangent line, and delta y is the difference in the y values on the function itself. However, the independent variable dx and delta x are the same. So the differential for the independent variable dx is the same as delta x. The change in the independent variable on both the linear approximation function, the tangent line, and the function itself are the same. Let's take a look now at what we used that for. Again, we used the value of dy in order to approximate the value of delta y. We used the change in y values on the tangent line to approximate the change in y values on the function itself. We're going to see that as the change in x went to 0, dy became equal to delta y, but it was a limit. We're going to extend the same idea to a function of more than one variable, including that abuse of notation. So we're going to define what's called the total differential rather than the differential. And this is because we now have more than one independent variable. We start with the two-dimensional domain in three-dimensional space. Let z be a function of x and y with some point x naught, y naught in the domain of f. Again, coming probably from a subset of R2, the xy plane. Let delta x and delta y be chosen so that x naught plus delta x, y naught plus delta y, is also in the domain of f. If the function is differentiable at the point x naught, y naught, then we say that the differentials dx and dy for the two independent variables are defined as delta x and delta y, similar to what we saw with functions of a single variable. The independent variable differentials are the same whether you're on the linear approximation function or whether you're on the actual surface itself. However, this is not true for dz and delta z, the dependent variable differential. dz is going to be the change in z value on the tangent line approximation. Delta z is the actual change in the function values on the surface. And again, as the change in x and the change in y go to 0, dz approaches the value of delta z. dz can be written as the partial with respect to x at the point times the differential dx plus the first partial with respect to y at the point times dy. Or we can leave off the point and simply write f sub x dx plus f sub y dy. Notice that we're not using the partial notation for those differentials. We're using the italicized letter D to represent the ordinary derivative. Let's now talk about what delta z actually is. We've talked about what dz is, which is the change in the values on the tangent line or tangent plane approximation. What is delta z? Well, delta z would just be the change in the z values from the point where we computed the tangent plane, x naught, y naught, to the point where we scooted over a little bit. In other words, you just have to plug both values into the function and subtract their z values. We can also extend this idea for functions of more than two variables as well. Let's suppose we're in four-dimensional space with w as a function of x, y, and z. Then the total differential would be the first partial of g with respect to x times dx plus the first partial with respect to y times dy plus the first partial with respect to z times dz. Remember that dx will be the same as delta x, and dy will be the same as delta y, and dz will be the same as delta z. In this case, though, dw is not the same as delta w, but as dx, dy, and dz, or delta x, delta y, delta z, go to 0, they become infinitely close. Let's look at our last example, number 3. We want to find the differential, the total differential dz of the function given by 4y squared plus x squared y minus 2xy. And we want to use it to approximate delta z, the true change in the z values at the point 1, -1. We're told that we're wanting to move over in delta x by 0.03 and delta y by -0.02. In other words, we're comparing the value at the point 1, -1 with the value at 1.03, well, what would that be? -1.02. The true change in the z value would require substituting both ordered pairs into the function, calculating the z value and subtracting them. What we want to do instead is use the total differential to approximate it by finding dz. The formula for dz can be found here. And again, I have gone ahead and substituted in that we want to find the first partial at the point 1, -1. where we're finding the tangent plane approximation. Go ahead and pause the video to work this one out, then turn the video back on so we can compare our results. The first thing that we need to do is find the first partials with respect to x and with respect to y and evaluate them at 1, -1. In this case, the first partial with respect to x is 2xy minus 2y. When we substitute in the domain value, we end up with 0, which means that the slope of the trace of the slope of the tangent line of the trace at that point is 0, meaning it's, well, not slanted. All right, let's look at the first partial with respect to y. That should give us 8y plus x squared minus 2x. When we evaluate that at our domain point, we get -9. The total differential is the change in the z values on the approximation, dz. This does not require us to know what the actual z value is. It just requires the information about how much you moved over with respect to x and how much with respect to y. Our dx or delta x is 0.03, and our dy or delta y was given to us at -0.02. We can then find the total differential by multiplying the value of the first partial times the associated differential. This gives us a dz value of 0.18. This is the change on the tangent line approximation between the z values evaluated at 1, -1 and evaluated at 1.03, -1.02. Let's see what the true difference is in the z values on the surface. To find that, what we need to do is compute the actual function value at those two different points. So to compute it at 1.03, -1.02, and it looks like I left out my zeros here, so I'll add these back in real quickly. 0.02, not sure how that happened. When you add those in, you get 5.180682. When we substitute the value where we computed the tangent plane approximation, 1, -1, we get a value of 5. Subtracting these gives us 0.180682 as the difference in the z values on the surface. In this case, our approximation is really quite close out to the third decimal place. This is the end of this particular section on the tangent planes and the linear approximation function using tangent planes. In the next section, we'll be discussing the chain rule. That's right, when you take derivatives and you have functions of functions, composition, you know you're going to have to involve the chain rule. As we'll see, it is more complicated when you have multiple independent variables. I'll see you for the next video in this series.